Welcome back. So this video, we're going to talk about percent composition. So first of all, you're well aware of what percents are, right? Percents can be defined as the part over the whole, right? You see percents all the time in your grades and so on and so forth. It's how many points you earned over how many total points there were, the part over the whole. So the percent composition, when we're talking about compounds, is basically a measure of the relative abundance of each element in a particular compound. Like how much, what proportion of the mass of that compound does that element contribute? Okay, so there's a couple different types of examples you might run into this. Percent composition if you're given the chemical formula or the name, right? So if you're given the formula or you come up with a formula, like for example, for sodium chlorate, calculate percent composition, that basically means, okay, what percent of this mass in this formula is from sodium, what percent is chlorine, and how much is from the oxygen. So in order to do that, what we want to do, remember, it's the part over the whole. So we need to figure out, okay, what is the molar mass of this compound? And then we just take each element's contribution and divide it by the whole and turn it to a percent. So for example, if we want to find the molar mass, we got one sodium, it's 22.99 grams. We have one chlorine, it's 35.45 grams. And we have 3 oxygens, that's 3 times 16, or around 48 grams. We add all that up in our calculator, and you get a molar mass of roughly 106.35 grams, is the same as 1 mole of sodium chloride. Now, to find the percent composition, we're going to take the parts and divide them each by the wholes. So the sodium contributed 22.99 of that. We take its contribution over the whole and multiply it by 100 to turn it into a percent. So 22.99 divided by 106.35 times 100, and it becomes 21.6%. Now, one question you might have, hey, do I care about significant figures on this style of problem? Is like, no, because all of these things came from the PR table. There's no experimental data here. We do the same thing for the chlorine and the oxygen. Chlorine is going to be 35.45 grams of chlorine over the total times 100. And then the oxygen is going to be its contribution. So it contributed 48 grams over the whole times 100. So calculate this as 33.3% from the calculator. And you could get the oxygen's contribution 2 different ways. Right, you do it this way, 48 divided by 106.35 times 100, or add these 2 things together and subtract it from 100, because these 3 percentages, right, should add up to 100%. If they don't, if you do it this way, and then you add them up just to double check your answer, and it doesn't come close to 100, you did something wrong. So that's one way to check these. Anyway, this one happens to be 45%, or 45.1, somewhere around. If you add these up, these actually add up to 100. Sometimes they are 100, sometimes they're 99.9, sometimes 100.1. Just, they should be around 100. Okay? We go to this next one. Key thing to understand here, we need a formula. And hopefully if you're looking at this, MgNO3, is that magnesium nitrate? Of course it isn't. Silly. We need 2 nitrates. Magnesium plus 2, nitrate is minus 1. So we need to figure out, we got 3 elements contributing here. We've got 1 magnesium, that's 24.31 grams. We've got 2 nitrogens, 2 times 14.01 grams is roughly 28.02 grams of nitrogen. And then we've got 2 times 3, or 6 oxygens, 6 times 16, or roughly 96 grams from the oxygen. So we get our total molar mass. We add those 3 things up. total mass, and now we do the same thing. Magnesium's contribution is 24.21 grams divided by 148. The nitrogen is the 28.02 grams over the 148.33. And the oxygen is the 96 over the 148.33 grams. So we get, and all these things get multiplied by 100. Put this in your calculator. This is roughly 16.4%. This is roughly 18.9%. And this can be found either by adding these two things together, subtracting by 100, or doing this calculation here. It's about 64.9-ish. 18, 12, 6, 8, 9. So you add these up and it's going to be like 100.2 or something like that. Close enough. Okay, but that would roughly be the percent composition for the magnesium nitrate. Now, here's a different style of a problem. So calculate the mass of an element in a compound using percent composition. So you notice, ooh, this example here is talking about magnesium nitrate. Well, that's luckily for us, we just did in our prior example, we found the percent composition of magnesium nitrate. So we're going to use that in this problem. This, however, right here, remember this has been measured. So we will have significant figures in this. So we have 23.5 grams of magnesium nitrate. And if you look back at example number 2, you notice that the mass, or the percent composition of this compound that was magnesium, which is basically what percent by mass this compound is magnesium, was 16.4%. So that means, right, what does a percent mean? So if you know that something is 16.4% magnesium, that is another way of saying, hey, if you have 100 grams of this compound in this case, so which for every 100 grams of magnesium nitrate you have 16.4 grams of magnesium. That's what this means, is like for every 100 grams of this compound, you have 16.4 grams of magnesium. And that is going to be your conversion factor for this. Right. So for every 100 grams of magnesium nitrate, we have 16.4 grams of magnesium. And you notice we're just multiplying it by this percentage converted back into a decimal. So we should have 3.85 grams of magnesium in that material, that sample. Now, let's go on to this next example. So let's say that you are running a jeweler store, and jewelry stores typically buy jewelry, used jewelry from people who don't want it anymore. And right, hopefully you're aware that jewelry, like if we're talking about metal, precious metals like silver, gold, platinum, whatever, they're sold in purities. Like in this example, we have got gold bracelet, and we're looking at, okay, if the bracelet weighs itself 12 grams, if it's 24 karat, how much gold would that be? And if it was 14 karat, how much gold would that contain? Because you would lose money as a jeweler if you're purchasing things, you're paying the same rate. If you were assuming everything was 24 karat versus 14, and if you're paying one rate for everything, people are not going to sell you anything more purified and what have you. And you've got this information over here in this table, which just kind of tells you a little bit about the purity of gold in the carats. But in part A, if we assume that this 12 gram bracelet, and if we said it was 24 karat, well, that means the purity is 99.9% gold, right? Which is pretty pure. So there's a couple ways to do this, right? You could just multiply this by this percentage changed back into a decimal, which would be 0.999. Or, you know, if you want to be thinking about it this way, one way you can think of this, if you have 12-gram bracelet, or 24, if you have 24 grams of 24 karat gold, I'll just use 24 karat AU for gold. In this case, for every 100 grams of 24 karat gold you actually have 99.9 grams of true gold. Right, that is the same as multiplying by this. And this just happens to work out with units. So 12 times 99.9 divided by 100. Or, again, you've got two single figures there, so it just rounds. You know, calculator says 11.988, two single figures. Basically, you've got 12 grams of gold. Now, if we do the same example, but if the gold is 14 karat, well, you notice the purity is much decreased. So if you have 12 grams of 14 karat gold, and the purity is 58.3%, so that means for every 100 grams of 14 karat gold, you have 58.3 grams of actual gold. Or roughly 6.996, or you just round that to two single figures. You actually have 7 grams of gold. So you can see, same bracelet, if it was 24 versus 14, almost double the amount of gold in the 24 karat. So you would be taking a loss if you paid the same rate. Now, the third style of problem you might see on these experimental things is you're given actual lab data, and you want to determine the percent composition. So, you're told that this compound contains only magnesium oxygen, and you got 13.6 grams. Well, so I need to find the percent composition of these two things. 5.40 grams of this was determined to be oxygen. Well, hopefully you understand, if I want to figure out, okay, the mass of the oxygen is 5.40 grams, and percent composition, or percent, is the part over the whole. So the oxygen part is kind of easy to figure out what its percent composition is. You put that over the whole. And the magnesium you can find two different ways. Right? If you wanted to figure out how much magnesium was present, right, you just take the 13.60 grams, subtract off the 5.40, and then divide it by the 13.60. So put this in the calculator, multiply it by 100, and that becomes 39.7% oxygen. Well, if you found this, the percent composition of magnesium, you know this plus this have to add up to 100, so you could subtract this from 100 to get 60.3%. Or you can do this as well, the 13.6 minus the 5.4. This up here becomes 8.20 grams, and then if you divide that by 13.6, well, you get 60.29% or 60.3 rounded to 3 single figures. Okay, so that's another style of problem that you might run into. Now in this one, it's got 3 elements: carbon, hydrogen, chlorine. You notice we're not giving a total mass, but we can find them total mass because we just add these 3 things together. But given how much of everything we have, and if we add these 3 things together, we're going to calculate 5.34 plus 0.42 plus 47, get around 52.8 grams total. So that goes here, here, and 58.2 down here, and everything here gets multiplied by 100. So then we just have to put it into our calculators. This divided by this times 100 becomes 10.1%. Right, this has 3 single figures because these two have 3. Right, this mass over here only has 3 as well when you add them together because this has two decimal places, this has 2, this only has 1 decimal place. So when you add them all together, it can only have 1 decimal place. This one here, 0.42 divided by 52.8. This one we have to round to only 2 significant figures because the 0.42 only has 2. And the last one, we can have 3 significant figures. We get 89.0. Okay. Now, one last topic that goes along with this. We want to talk about hydrates. And hydrates are ionic compounds that include water within their crystal structure. And you've worked with some hydrates already, but you just haven't noticed that they were hydrates or needed to know or anything. But a hydrate, if you see a hydrate, you notice this would be its formula. Right? This is, and we want to be able to name these. Right? Hydrates are ionic compounds, so this part is ionic. And then you notice this dot, and then how so many waters this is the hydrate part. But these things will form a crystal structure, including water in it. And that water can either be part of the crystal structure where it's called a hydrate, or if you drive off the water, which we'll do in the lab in a couple of class periods, when you drive off of the water from a hydrate, it becomes, instead of a hydrate, it's now an anhydrous form of that hydrate. Anyway, but we name this part just like an ionic compound, so CuSO4 right, is copper 2 sulfate, and we have to include the 5 waters. So water, you know, is, well, we're not going to put the name water in this. We're going to change that to hydrate, but we need to communicate how many waters are present, and we use the covalent naming prefixes. So 5, remember, is penta. So copper 2 sulfate pentahydrate would be the name of this compound. You see FeSO4.7H2O. Well, it's iron 2 sulfate. That's how you name the first part. And then 7, the prefix is hepta. So iron 2 sulfate heptahydrate. And lastly, CuCl2.6H2O. Well, this is copper 2 chloride. And the prefix for 6 is hexa. So this is hexahydrate. All right, so if we want to figure out the percent water in nickel 2 sulfate hexahydrate, now first of all, we need to be able to go from this formula, name to a formula. So it's NiSO4, and that's nickel 2 sulfate, and hexa is 6, so it's NiSO4.6H2O. So one common use of percent composition is when we want to figure out how much water would be part of the hydrate. And remember, percent is the part over the whole. So the strategy for these problems is I need to figure out what the entire weight, basically the molar mass of nickel 2 sulfate hexahydrate is, and then figure out how much 6 waters weigh, and then divide the two. Okay, so the first step is we need to figure out the molar mass of nickel 2 sulfate and the 6 waters. So we've got 1 nickel, which contributes 58.71 grams. We got 1 sulfur, 32.06 grams, 4 oxygens, so that's 4 times 16, roughly 64 grams of oxygen. And we've got 6 waters. And I'm just going to group keep the waters by themselves. So we've got 6 H2Os. Right. As you get more practice with molar masses for the rest of the year, there's certain things that you'll probably just come to memorize or just have memorized from use. The water happens to be one of them. And the molar mass of water is roughly about 18.02 grams. You got 16 from the oxygen, 2 hydrogens, that's 18.02. So 6 times 18.02 grams. So the water contributes 108.12 grams from the water. These things contribute or roughly the molar mass of the whole thing is 262.89 grams. And the water's the percent of that, or the mass of water in that compound is this 108.12 grams of water. So I can figure out the percent of this. And that comes out to be roughly 41.1% water. That means the rest, the nickel sulfate contributes the rest of it, or 58.9%. You could even break that further down and figure out the percent that is nickel, percent that's sulfur, and percent that is oxygen, if you so chose. But this problem didn't ask you to do that. It just said percent water. So on this problem here, it said a student heated 1.75 grams of the hydrate of calcium chloride and found it to have this mass after heating. It said calculate the formula of the hydrate and the percent water in the hydrate. So this one is going to be a little bit more involved, but our total mass of the hydrate is 1.75. We found that after heating, which means after you drive off all the water, you've got 0.89 grams left over. That's calcium chloride. So the mass of the water, is the 1.75 grams they started with minus the 0.89 grams of the calcium chloride. So now we've been able to determine that of that 1.75 grams that we started with, 0.89 grams was calcium chloride, 0.86 grams was water. So the percent water part is super easy. We can already do it. Percent water is just going to be the 0.86 grams of water over the whole, which is 1.75 grams, times 100. Or roughly 49%. You can only have two same figures because of the 0.86. Now, this next part of this problem is, you probably want to revisit this after we go over empirical molecular formula. So I'm going to show you how to do this part now, but it involves some of this empirical molecular formula that we'll get to in the next video or the next part of the notes. So, the way we approach this is that we need to convert both of these masses into moles for each one. So, for example, 0.89 grams of calcium chloride. We want to figure out how many moles that represents. We need a mole conversion. So we need a molar mass. with calcium chloride. So mole mass of calcium chloride 70.9 is the Cl2, and the calcium 40.08. So the molar mass is 110.98 grams. So we've got 0.0080 moles of calcium chloride. Do the same thing for the water. 0.86 grams of water. And we know that 18.0 grams of O2 grams is the same as 1 mole. 0.86 divided by 18.02. And you've got roughly 0.0477. No, 0.4477. So you're going to round that to 0.048 moles of H2O. Now, basically what we want to be doing is, in a hydrate, right, it's the formula of hydrate is going to be CaCl2 dot some number times H2O. And this number here would represent basically this value in front of this, and this here would represent this. But you notice this value here has to be basically 1 mole. For every 1 mole of calcium chloride, basically how many moles of water do you have? Well, the way to get this into 1 mole is I'm going to divide both these values by this number. Because 0.0080 moles divided by 0.0080 is 1. If we do this divided by 0.0080 moles, you get a value of 6. So now we know that this hydrate is calcium chloride hexahydrate. Okay? Like I said, this little knowledge here is basically using this empirical molecular formula strategy that we're going to cover in the next video. So don't worry if this doesn't make sense to you. This bottom part doesn't make sense to you. This top part should. This is just percent by mass. This part will make more sense as you finish the empirical molecular formula.